the binomial expansion. Let me start by going through some basic terminology. So first, what is a binomial? So any expression in the form a plus b, which consists of two terms, and there is plus between them, forms or represents a binomial. Binomial, it means that there are two terms. Now, we are going to be interested in the expansions of the powers of binomials. So a power of the binomial is, for example, a plus b to the power of 2, or a plus b to the power of 3, like you can see here. So in general, a plus b to the power of n, where n is the integer, represent what we are going to be interested in. And actually we are going to be interested in the expansion of those powers. And there is a shorthand. Instead of saying that we are going to talk about the expansions of powers of binomials, we just simply say that we are going to study the binomial expansion. Okay, binomial expansion. So binomial expansion is the expansion of the power of the binomial, any integer power, so actually the natural number power of the binomial, like you can see here. Okay, so let me now try to look at how this works and try to find some pattern. Okay, so let me start with the power of a plus b to the power of 2. A plus b to the power of 2 can be understood as a plus b times a plus b, as you well already know. And this can be calculated, and I'm going to calculate it and write it especially here in a very special way. It can be calculated by multiplying each term of the second bracket by each term of the first bracket. So I will now choose the first term of the first bracket and multiply both this term and this term and write them in one single line. So it's a times a, it's a squared, plus a times b, so it's ab. And now what is interesting, I'm going to use the second term in the first bracket and multiply the first and the second and write it below in a special way. So b times a is ba, but you can write it as ab and write it below this term, so it's ab, plus b times b is b squared. You can see what I did. I wrote those two lines here. The first line represents multiplication by the first term in the first bracket, and the second line the multiplication in the second term in the first bracket. Now you can see that when you add those two, you have a squared, you have just once, so it's a squared. Then you have this term twice, so it's plus 2ab, and finally you have just b squared once. And what you got is the binomial expression a plus b all squared. So the one which is here, it's a squared plus 2ab plus b squared. Now we can use this method and try to calculate a plus b to the power of 3. A plus b to the power of 3. And we can use the information obtained from the previous step, because a plus b to the power of 3 can be understood as a plus b times a plus b to the power of 2. Okay, so we can use the expansion of a plus b to the power of 2 and express the expansion of a plus b to the power of 3. And again, I'm going to use two lines to express this. So first I multiply by the first term in the first bracket everything which is here. But before I do it, of course, I need to replace this by what I got here. So it's a plus b times bracket a squared plus 2ab plus b squared. And now it's time to write it in two lines, so sorry for that. So now I multiply by a, this, and this, and write it in one single line. So it's a times a squared is a cubed. Now a times 2ab is plus 2a squared b, plus, and you have a times b squared, you have ab squared, like this, plus, and now go to the second line and multiply by b. So it's b times a squared, b times this, and b times this. So it's b times a squared is a squared b, and I will write it below, plus, and we have b times b squared, which yes, we have b times 2ab, which is 2ab squared, 2ab squared, plus, and we have b times b squared, which is b cubed. You see, the similar expressions are below each other, and yet I can now take those and add them together. So a cubed is alone, so I just copy it, plus we have 2a squared b plus a squared b, which is 3a squared b, plus we have one piece of this and two pieces of this, so we have 3ab squared, plus, and we have just one b cubed. What we got is the expression for a plus b all cubed. It's a cubed plus 3a squared b plus 3ab squared plus b cubed, and this should be the same as the expression written here. Okay, now let me see what happens if I want to calculate a plus b to the power of 4. I can do it very similarly, and why do I do it? I want us to see an emerging pattern. There is a pattern that we have to try to see, to have an insight into it, and to develop it we need to repeat it a little bit, so maybe for this time, or you will see later. Okay, so a plus b to the power of 4. It should be, according to the previous considerations, a plus b times a plus b to the power of 3. Okay, but we know what a plus b to the power of 3 is already, so I can write it. It equals a plus b times, and now I can copy a cubed plus 3a squared b plus 3ab squared plus b cubed, like this, and I can write into two lines what I get when I multiply by the first and then by the second term in the first bracket. So multiplying by a all four terms in this bracket, I get the following. I get a times a cubed is a to the power of 4 plus a times 3a squared b is 3a cubed b plus a times 3ab squared is 3a squared b squared, 3a squared b squared, plus a times b cubed is ab cubed, plus, and into the second line I'm going to write what I get by multiplying b times each term in the second bracket, like that. So it's b times a cubed, I will write it below this, so it's a cubed b just once, plus b times this is 3a squared b squared, 3a squared b squared, plus b times this is 3ab cubed, 3ab cubed, plus, and b times this term is b to the power of 4. Okay, and now you can see that by adding those lines, what you get, you have one single a to the power of 4. Now 3 and 1 give you 4, so it's plus 4a cubed b, plus you have 3 plus 3, it's 6a squared b squared, plus you have 1 and 3, you have 4ab cubed, plus b to the power of 4. And this is the expression for a plus b to the power of 4. So you see, here it is. So now the most difficult part. We should be able to find something common in all those expressions. So let us start with the one here. A plus b squared. I will look at it and I will use blue color to write it in a different way. So a squared can be written as a squared times b to the power of 0. Okay, why? Because b to the power of 0 is just 1, and a squared times 1 is just a squared, plus 2a to the power of 1, b to the power of 1, plus, and here we have a to the power of 0 times b to the power of 2. So you see, you have three terms. When you have a plus b to the power of 2, you have three terms. Okay, three terms altogether, and each of those terms contains some power of a multiplied by some power of b. What you can notice is that the powers of a start at 2 and then decrease by 1. So it's a to the power of 2, then a to the power of 1, a to the power of 0. As you can notice also, the powers of b start at 0 and then increased by 1. So b to the power of 0, b to the power of 1, b to the power of 2. Is it similar when you have a plus b to the power of 3? Let us see. First, we notice that we can replace it or rewrite it in the following way. A to the power of 3 times b to the power of 0, okay, because it's 1, plus 3a squared b to the power of 1, plus 3a to the power of 1 b to the power of 2, plus a to the power of 0 times b to the power of 3. Okay, so how many terms do we have? 1, 2, 3, 4. We have 4 terms. Okay, 4 terms altogether. We had the power 3 and we have 4 terms. Here we had power 2 and 3 terms. So the number of terms seems to be 1 more than the power of the expression of the binomial. Okay, so it's 4 terms. Now you see that the powers in a decrease by 1, so it's a to the power of 3 to the power of 2 to the power of 1 to the power of 0, and the powers of b increase by 1, b to the power of 0, b to the power of 1, 2 and 3. Let us see whether it's the same here. So if our hypothesis is correct, we should have 5 terms. Okay, 1, 2, 3, 4, 5. There are really 5 terms. I can rewrite them. A to the power of 4 times b to the power of 0 plus 4 times a to the power of 3 b to the power of 1 plus 6 times a to the power of 2 b to the power of 2 plus 4 times a to the power of 1 b to the power of 3 plus a to the power of 0 b to the power of 4. So altogether we have 5 terms. Okay, so it's one more than the power of the expression, and again the powers of a decrease by 1, so a to the power of 4 to the power of 3, 2, 1, 0, and the powers of b increase by 1, b to the power 0, 1, 2, 3 and 4. Okay, so there is a pattern in regard to the powers of a and b in all those expansions. Okay, then there is the pattern as in regards to the number of terms in each expansion. But now the most interesting part, and that is the part about the coefficients. So here I have the coefficients of 1, 2 and 1. Okay, so this was taken once, twice, once. Here I have the coefficient 1, 3, 3, 1. Okay, and here the coefficient 1, 4, 6, 4, 1. So how exactly were those coefficients obtained? Okay, so you see the expression a plus b to the power of 1 has just the coefficients 1a to the power of 1 b to the power of 0 plus 1 a to the power of 0, b to the power of 1. This even holds true for the power of 1, you can see. So these coefficients were 1 and 1. And you see what happened here. 1 got here as just 1 times a squared. 1 and 1 from this term and this term became 2, and 1 became 1 here. So imagine having numbers 1 and 1 below each other like this, and imagine adding them together. So coefficient of 1 and 1, 1 and 1, when you add them you get 1, 2 and 1. So this is the pattern. You got 1, 2, 1 here, 1, 2, 1, you can see it. Now imagine what were the coefficients here in this line. The coefficients were 1, 2, 1, 1, you can see 1, 2, 1, and below there were the coefficients again, 1, 2, 1. 1, 2, 1. These coefficients had to do with the fact that the coefficients of a plus b squared were 1, 2, 1. And now by adding those, I got the coefficients of this final expression. So it's 1, 2 plus 1 is 3, 1 plus 2 is 3, and you see just 1 here. Okay, so it's 1, 3, 3, 1. Now, when you look at this, you see the coefficients 1, 3, 3, 1. So I can write them here, 1, 3, 3, 1, and below 1, 3, 3, 1, 1, 3, 3, 1. When you add them together, what you get is 1, 3 plus 1 is 4, 3 plus 3 is 6, 1 plus 3 is 4, and 1. Okay, so this pattern of coefficients 1, 4, 6, 4, 1, or 1, 3, 3, 1, and so on, it has to do with something familiar to you already. And this familiarity stems from combinatorics, from the previous topics from the autumn, and it had to do with combinational numbers, or with Pascal's triangle. So what does it mean to add numbers 1 and 1 in this particular way by shifting the second line to 1 to the right? What you can do instead of adding these, you can do the following. You can write, and I will use another color here. Let me use this. You can write the pattern 1, 1, 1, and now you can add 1 plus 1, it's 2, and write it below. Now you can add 1 again and 1 again, and you can add 1 plus 2, which is 3, 2 plus 1, which is 3, and add 1 here and here. So you can continue like this. You can add 3 plus 3, it's 6, 3 plus 1, it's 4, 3 plus 1, it's 4, and add 1 here and 1 here. And what you get are precisely the same patterns. So this line of the triangle, this is the so-called Pascal's triangle. This line of the triangle contains the coefficients of a plus b to the power of 2. This line contains the coefficients of a plus b to the power of 4. Sorry, to the power of 3. And this one, the coefficients of the expansion a plus b to the power of 4. Now, how does it work? You see that this, adding these 1, 1 and 1, 1 like in this position, is equivalent to adding 1 and 1 and writing it below, because this number 2 was obtained actually by adding this number and this number, okay? Because this is this and this is this. So these two numbers were added, combined. So this number 3 here consists in adding 2 and 1, but this number 2 is okay, but number 1 is here. Number 1 is here. So 1 and 2 is 3. This number 3 was obtained by adding 2 and 1. So it's the same as if I added these two numbers. You can see it. Okay. Numbers 1 on the sides always appear without change. They are there in each situation. They represent those isolated terms, a squared, a cubed, a to the power of 2, and so on. Okay, so this is how it works. This is the pattern, and now we can try to generalize it and provide some final words about that. So let me write again a plus b to the power of 4. It was a to the power of 4 times b to the power of 0 plus 4 times a to the power of 3 b to the power of 1 plus 6 times a to the power of 2 b to the power of 2 plus 4 times a to the power of 1 b to the power of 3 plus 1 times a to the power of 0 b to the power of 4. This was the expansion. I can write the coefficients here. So this was the particular case that we studied, and now in general, for the expansion of a plus b to the power of n, where n is a natural number, we can see that as we look from left to right across the expansion, from left to right, the powers of a decrease by 1, so 4, 3, 2, 1, 0, this is what they mean, while the powers of b increase by 1, 0, 1, 2, 3, 4. This works. Now, the sum of the powers of a and b in each term of the expansion is n, so it should be 4 in our case. So if you add 4 plus 0, you get 4. 3 plus 1, you get 4. 2 plus 2 is 4, 1 plus 3 is 4, 0 plus 4 is 4. So the sum of the powers of a and b in each term of the expansion is n. Then the number of terms in the expansion is n plus 1. You see, we had the power of 4, we had 5 terms. And this is a general pattern which will hold for all the other. You can see it. You can imagine repeating this process on, and you see that if we had the 5th power, we would get one more term. Okay, so then it means that there would be 6 terms for the 5th power, and so on and so on. So the number of terms is always n plus 1, and the coefficients of the terms are rho n of Pascal's triangle. So in our case, the coefficients 1, 4, 6, 4, and 1 are rho 4 of the Pascal's triangle. So we can call the rows like, you know, this is the row 4, this is the row 4, this is row 3, this is row 2, row 1, and we have the row 0. So this is what we call the rows of the Pascal's triangle, and we can continue. So for example, the 5th row would be 1, 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and 1 in the end. So these numbers are the 5th row, the row 5 of Pascal's triangle. Okay, this is the Pascal's triangle. Okay, so this is what you need to know about binomial expression at the moment, and this knowledge then should be applied to solve the problems of today's problem set.